Libya has no rivers, almost no rain, so it stunned the world by building a 4,000-kilometer artificial river beneath the Sahara. In the 1950s, a desperate search for oil struck something even rarer, one of the planet's largest fossil aquifers, a hidden water source locked under the desert for millennia. Within decades, engineers pulled off a $25 billion feat, moving ancient water from 1,300 wells to keep coastal cities alive. Today, this buried lifeline supplies millions, but the great man-made river isn't infinite, and threats, from war to sabotage, now endanger every drop. If Libya could conjure a river where nature gave none, can it keep water flowing when time and the sand are running out? Oil drillers in the Libyan desert expected to strike black gold. Instead, their boreholes tapped into something almost mythical, a vast ancient sea trapped beneath the sand. This was the Nubian sandstone aquifer system, a hidden reservoir stretching across Libya, Egypt, Sudan, and Chad. The first drill cores, pulled up in the 1950s, revealed water that had not seen sunlight for thousands, even millions of years. Scientists soon realized the scale. This was not a pocket, but one of the world's largest underground water reserves, holding more than 150,000 cubic kilometers of fossil water. In Libya's portion alone, estimates put the accessible volume at up to 8,000 cubic kilometers, enough to fill Lake Erie several times over. Yet this discovery came with a catch. The water was classified as fossil for a reason. It had collected in wetter ages long before the Sahara became a desert, and it barely recharged under today's arid climate. Hydrologists confirmed the flow was almost entirely one way. Once pumped out, the supply would not return on any human timescale. Isotope analysis and well logs from the first deep tests at Kufra and Saria confirmed the water's age. Some samples clocked in at nearly 1 million years old. For a country with no permanent rivers and less than 50 millimeters of rain a year, the implications were immediate and profound. Here was a lifeline buried under the world's harshest desert, running silent and unseen for hundreds of kilometers. But it was a lifeline with a countdown. Libyan officials, faced with a swelling population and shrinking coastal aquifers, began to see the aquifer not just as a geological curiosity, but as the only realistic answer to the nation's water crisis. The question was no longer whether the water existed, it was how to reach it and how to use it before time and the desert ran out. By 1984, Libya stood at a crossroads. Coastal aquifers were collapsing under the weight of saltwater intrusion, and the population had doubled in just 2 decades. The government made a decision that would rewrite the country's future, to build a river where none existed, and to do it on a scale no one had attempted before. The Great Man-Made River Project was approved that year by national decree, launching what would become the world's largest water transfer scheme. The vision was simple: move ancient water from deep beneath the desert to the cities where it was needed most. But the risks were immense. The entire project would be financed domestically, drawing from Libya's oil revenues and a patchwork of taxes on everything from cigarettes to airline tickets. No foreign loans, no external guarantees. The price tag soared past $25 billion, a sum that rivaled the national budget. To oversee the undertaking, the government established the Great Man-Made River Authority. This body would coordinate every aspect, from drilling wells hundreds of meters deep to laying thousands of kilometers of pipe through the Sahara. Construction began in the eastern desert, with the first phase linking the Saria and Taza well fields to the coastal cities of Benghazi and Sirte. By August 1991, water began flowing through the new arteries, reaching Benghazi's taps for the first time. 5 years later, in 1996, Tripoli, the capital, was connected to the grid, ending decades of water rationing and uncertainty for millions. Each milestone was met with national celebration, but the challenges behind the scenes were relentless. The logistics of moving concrete, steel, and heavy machinery across shifting dunes pushed engineering teams to their limits. Yet the promise was too great to ignore: a stable water supply for cities that had always lived on the edge of drought. The great man-made river became more than infrastructure. It was a statement of intent, a wager that technology and determination could outlast the desert. With the system operational, Libya's urban centers began to grow with a confidence they had never known before. The next challenge would be to turn this lifeline into a permanent solution, and to protect it from the pressures that lay ahead. Stretching across the Sahara, the great man-made river is a feat of engineering with few rivals. Its arteries, over 4,000 kilometers of buried pipeline, run farther than the distance from London to Baghdad. This network is not a single line, but a system of corridors, each designed to move water from deep desert well fields to Libya's crowded coast. More than 1,300 wells, most drilled over 500 meters down, feed the system. Each well taps into water that has waited underground for millennia. The project was built in phases, each one a module stitched onto the last. Phase 1 began in the east, linking the Sahara and Tazarbo well fields to Benghazi and Sirte. Water first reached Benghazi in 1991. Phase 2 reached west, connecting the Jabal Hassauna fields to the Jafara plain, bringing relief to Tripoli and Misrata. By 1990s, the capital's taps were supplied by water pulled from the heart of the desert. Later phases were planned to extend the reach even further. Corridors from Ghadams to Zuwara and Zawiya in the west, Ajdabiya to Tobruk in the northeast, and a link between Kufra and Tazarbo. Some of these extensions remain unfinished, stalled by conflict and shifting priorities, but the main east and west trunks still anchor the system. At full design, the river was meant to deliver up to 6.5 million cubic meters of water every day. That's enough to fill 2,600 Olympic swimming pools day after day, year after year. Massive reservoirs along the route buffer supply and demand, while the branching corridors allow water to be routed where it's needed most. On a map, the system looks like a circulatory system for an entire nation: arteries, veins, and capillaries, all pulsing with ancient water. The scale is difficult to grasp: a hidden river, built not by nature, but by ambition and necessity. A single segment of the great man-made river's main pipeline weighs as much as a city bus and stretches 7 meters from end to end. Each one is a pre-stressed concrete cylinder pipe, 4 meters wide, steel at its core, reinforced with tightly wound wire, then encased by high-strength concrete. More than 500,000 of these giants were cast at custom-built factories in Brega and Sahara, their bell and spigot joints sealed with rubber O-rings and clamps for a watertight fit. The task of hauling them across the Sahara required its own feat: a 1,500-kilometer haul road built just for the convoys, with crews working in triple-digit heat and sandstorms that could bury a trench overnight. Laying the pipeline was a marathon of precision. Trenches up to 7 meters deep were carved into shifting sand, lined with soft bedding to protect each pipe from cracking under its own weight. Alignment tolerances were strict, less than 10 centimeters of leeway over hundreds of kilometers. Veteran engineers recall the tension of watching a crane lower each segment into place, knowing that a single misalignment could ripple trouble for years. One drilling chief, after months in the desert, described the moment water first surged through a finished line as watching a river come to life where there had only been silence. Strategic reservoirs were built along the route, some holding more than 24 million cubic meters, a safety net for cities and a buffer against pump failures. But the system's real nervous system lies underground. Every kilometer of pipe is protected against corrosion by cathodic protection, a network of electric currents that keeps the steel from rusting away in the salty desert soil. Above ground, a SCADA network, short for Supervisory Control and Data Acquisition, lets engineers monitor flow rates, pressure, and even leaks from control rooms hundreds of kilometers away. The combination of brute force and delicate monitoring turned a buried pipeline into a living network, but it also made every kilometer dependent on specialized parts and constant vigilance. As the years passed, the challenge would shift. Not just building the river, but keeping it alive when repairs became harder and threats more unpredictable. Hydrologists studying the great man-made river do not mince words. The Nubian sandstone aquifer is a finite inheritance, not a renewable resource. The water that flows from Libyan taps today began its journey underground in an age when the Sahara was green, and rainfall was measured in centuries, not drops. Scientific surveys confirm that the modern recharge rate is so low, it is practically zero. Whatever leaves the aquifer now is lost for good on any human time scale. Estimates for how long this ancient reserve can last vary, but most independent analyses converge on a sobering range. At current rates of withdrawal, Libya's accessible share could be depleted in as little as 60 years, or stretch, under strict conservation, toward a century. Official statements sometimes offer more optimistic timelines, but international agencies like UNESCO and the IAEA have consistently warned that the real horizon is much closer. The difference comes down to assumptions. If cities keep growing and demand holds steady, the clock ticks faster. If conflict or crisis slows usage, the end date drifts, but the direction never changes. The energy required to keep this river flowing is colossal. Each cubic meter of water must be lifted from depths of 500 meters or more, then pushed through thousands of kilometers of pipe. Technical estimates put the system's power appetite at over 1 billion kilowatt-hours per year, enough to run a mid-sized city. Every hour, pumps draw on the national grid, making water delivery as dependent on electricity as on geology. As water tables fall, the energy bill rises, and so does the risk of interruption. In the words of one hydrologist, it's a race between the pump and the well. The result is a fragile balance. The river keeps Libya's cities alive, but every drop spent is a drop that will not return. There is no second act for fossil water. The question now is not just how to protect the system from outside threats, but how to stretch its life in the face of an unyielding geological limit. On July 19, 2011, NATO jets struck the Brega pipe factory, the only facility in Libya capable of producing the giant concrete cylinders that hold the great man-made river together. In one night, the country lost its ability to manufacture or repair the backbone of its water supply. Replacement pipes, once made to order, now had to be imported at great cost and delay. For engineers in charge of keeping water flowing to Tripoli, every cracked segment became a crisis with no quick fix. 8 years later, a different threat arrived. In April 2019, armed men stormed the Hassana control station deep in the desert. They ordered the pumps shut down, cutting water to Tripoli and much of western Libya. Within 48 hours, taps in the capital ran dry. Hospitals began rationing, and city officials scrambled to deploy water trucks. One Tripoli water manager, awake for 3 days straight, described the scene as a city on the edge. Families queuing at dawn, rumors of unrest, and no timeline for restoration. The standoff lasted up to 10 days in some neighborhoods, affecting nearly 2 million people. Then, in May 2021, Station 353, another critical node, was blown up in an act of sabotage. 4 major cities lost supply overnight. Repair crews faced gunfire and threats as they tried to reach the site. For many, the outages stretched more than a week. Each attack exposed the system's fragility: a single factory, a single control room, a single pumping station. Anyone could bring the river to a standstill. The stakes were no longer just technical. They were immediate, human, and growing with every new crisis. Repairing Libya's buried river starts with the basics: patch the leaks, guard the nodes, and restore what's been lost. Engineers prioritize the oldest pipelines for rehabilitation, targeting segments where corrosion or sabotage have left joints vulnerable. Specialist crews inject grout into cracked bell and spigot joints, replace worn O-rings, and reinforce sections where shifting desert sands have exposed pipe to damage. Every fix is tracked through a remote monitoring network, with sensors alerting control rooms to sudden drops in pressure, signs of a breach or illegal tapping. But no amount of patchwork can compensate for a missing backbone. The Brega factory, once capable of casting hundreds of pre-stressed concrete pipes each week, remains only partially restored after the 2011 airstrike. Without full domestic manufacturing, every replacement segment must be imported at high cost and long delay. Plans are underway to rebuild Brega's production lines, with a focus on quality control and corrosion-resistant coatings for new pipes. Security is now as critical as engineering. Armed guards and surveillance drones patrol key pumping stations and control rooms, especially at vulnerable desert intersections. The goal: keep water flowing, even when politics and conflict threaten to turn the taps off. Each step, repair, rebuild, protect, buys time for a system stretched to its limits. Desalination plants dot the Mediterranean from Spain to Israel, but in Libya, they remain the exception, not the rule. The reason comes down to cost and energy. Pulling water from the great man-made river costs less than 20 cents per cubic meter, sometimes even lower when the system runs at full efficiency. Desalination, by comparison, ranges from $1 to $1.50 for every cubic meter produced, a price tag 4 to 6 times higher. The energy gap is just as wide. Pumping fossil water from underground uses less than 1 kilowatt-hour per cubic meter in many segments, while turning seawater into drinking water can require 4 or 5. For a nation where electricity supply is already uncertain, this difference matters. Yet the equation is changing. As the aquifer shrinks and pipeline repairs grow more expensive, the cost advantage of the hidden river begins to erode. Every cubic meter lost to leaks or illegal tapping makes desalination look less like a distant backup and more like an eventual necessity. Reducing losses through better monitoring, tighter enforcement, and infrastructure upgrades can buy time. But even the most efficient system will face hard choices. Libya's water future will depend not only on technology or energy prices, but on coordination with its neighbors who share the Nubian aquifer. In the end, the decision is not just about numbers, it is about how to keep the taps running when the old answers no longer fit. Libya's great man-made river stretches more than 4,000 kilometers beneath the desert, carrying fossil water drawn from the Nubian sandstone aquifer, one of the world's largest and oldest underground reservoirs. Built at a cost exceeding $25 billion, the system has supplied cities like Tripoli and Benghazi since 1991, using over 1,300 deep wells and massive pipelines. But the aquifer's water is not renewable on human timescales, with documented depletion estimates spanning from 60 to 100 years, depending on extraction rates. Since 2011, documented attacks, such as the NATO bombing of the Brega pipe factory and the 2019 and 2021 shutdowns, have exposed the network's vulnerability. Today, much of the system still functions, but faces ongoing risks from sabotage, power shortages, and maintenance gaps. The long-term future depends on pipeline repairs, securing infrastructure, and weighing desalination, which currently costs 3 to 6 times more per cubic meter. What remains unknown is how long Libya can sustain this flow before the limits of ancient water are reached. The evidence is clear: the river beneath the sand is real. Its survival is not guaranteed.